Chapter 15, Polyunsaturated Fats and Instability Risk. Polyunsaturated fats introduce multiple double bonds into the fatty acid chain, creating repeated bends that prevent close alignment within the membrane. Each double bond increases spacing between neighboring lipids, reducing packing density and increasing lateral movement. When incorporated into the bilayer, these structures expand the distance between molecules and weaken cohesive interactions that maintain membrane integrity. This does not immediately disrupt function, but it alters the physical conditions under which the membrane operates, shifting the system toward a more permissive and less constrained state. Instability emerges from how this altered structure behaves under load. Reduced packing density increases permeability, allowing ions and small molecules to pass more easily through the membrane. This weakens gradients that depend on containment, forcing the cell to expend additional energy to maintain separation between compartments. At the same time, increased fluidity reduces the mechanical resistance of the membrane, making it more susceptible to deformation under pressure and shear forces. These changes do not occur in isolation. They compound, affecting signaling, transport, and energy systems simultaneously because all of these processes depend on controlled membrane behavior. The presence of multiple double bonds also increases susceptibility to chemical modification. Each double bond represents a site where reactive species can initiate structural changes in the fatty acid chain. When these reactions occur, the resulting molecules no longer integrate into the membrane in a consistent way, further disrupting packing and increasing permeability. This creates a feedback loop in which structural instability promotes chemical damage, and chemical damage amplifies structural instability. Signal behavior shifts within this environment. Increased fluidity allows receptors and signaling molecules to move more freely, lowering the threshold for interaction. This can lead to excessive or unregulated clustering, amplifying signals beyond their intended range. At the same time, the lack of structural constraint reduces the precision of these interactions, introducing variability into signaling outcomes. The membrane no longer enforces consistent conditions, and the system begins to produce outputs that do not reliably correspond to input. Cholesterol attempts to compensate for this instability by inserting between lipid molecules and reducing excessive movement. However, its stabilizing capacity depends on the surrounding structure. In a membrane dominated by polyunsaturated lipids, the degree of disorder limits how effectively cholesterol can restore cohesion. The system remains more fluid and less controlled, even with regulatory input. Mechanical stress exposes these limitations further. Under conditions of deformation, a membrane with reduced structural density cannot distribute force effectively. Localized strain leads to areas of thinning and increased permeability, allowing uncontrolled exchange across the bilayer. This compromises the boundary function of the membrane, affecting processes that depend on stable separation between internal and external environments. Energy systems are directly impacted by this shift. Increased permeability leads to greater leakage of ions and protons, reducing the efficiency of gradient-dependent processes. Mitochondrial membranes, in particular, require tight control of proton gradients to sustain ADP production. Structural instability increases the energy required to maintain these gradients, reducing overall efficiency and placing additional demand on metabolic systems. Remodeling cycles determine the extent to which polyunsaturated fats influence membrane behavior. As these lipids are incorporated over time, they alter the baseline properties of the bilayer, gradually shifting it toward increased fluidity and reduced structural constraint. This process reflects sustained input rather than immediate change, embedding these characteristics into the membrane architecture. Polyunsaturated fats therefore act as structural modifiers that increase flexibility at the cost of stability. Their presence expands the range of motion within the membrane, but reduces the system's ability to maintain controlled conditions under stress. When their proportion rises beyond what can be stabilized by saturated lipids and cholesterol, the membrane becomes more permeable, more chemically reactive, and less capable of enforcing the boundaries required for precise function because the structural framework has shifted toward a state that prioritizes movement over containment. Structural fragility of multiple double bonds. Multiple double bonds introduce repeated disruptions along the fatty acid chain, preventing the linear alignment required for tight packing within the membrane. Each double bond creates a fixed bend that cannot straighten under normal physiological conditions. When several of these bends are present in a single molecule, the chain occupies more space and fails to integrate cleanly with neighboring lipids. This reduces cohesive interactions across the bilayer, increasing spacing between molecules and weakening the structural continuity that maintains membrane integrity. This structural irregularity affects how force is distributed across the membrane. In a densely packed bilayer, mechanical stress is shared across aligned lipid chains, allowing the membrane to resist deformation. In a membrane enriched with polyunsaturated lipids, the lack of alignment creates points where force is not evenly transmitted. These points become areas of localized strain, where the membrane is more likely to thin, bend excessively, or form transient defects. These defects increase permeability and disrupt the controlled separation between compartments. Chemical stability is also reduced. Each double bond represents a site where reactive species can interact with the fatty acid chain. With multiple double bonds present, the probability of these interactions increases. When a reaction occurs, it alters the structure of the lipid, creating products that no longer fit within the membrane in a consistent way. These altered molecules disrupt packing further, increasing the likelihood that adjacent lipids will also be affected. This propagation changes the physical properties of the membrane beyond the initial site of damage. The combination of structural irregularity and chemical reactivity creates a condition where the membrane is more susceptible to both mechanical and chemical stress. Movement within the bilayer becomes less constrained, and the ability to maintain a continuous, stable boundary is reduced. Ion gradients depend on this continuity. As gaps form more readily, ions cross the membrane with less resistance, reducing electrical stability and increasing the energy required to maintain separation. Protein behavior reflects these changes. Embedded proteins rely on a consistent lipid environment to maintain their structure and function. When the surrounding membrane becomes irregular and less stable, the mechanical context in which these proteins operate shifts. This alters how they transition between states, affecting signaling and transport processes that depend on precise conformational changes. Cholesterol can partially mitigate these effects by inserting between lipid molecules and reducing excessive movement, but its ability to restore order is limited by the degree of disruption present. When multiple double bonds dominate the surrounding lipids, the overall structure remains less cohesive and the stabilizing effect of cholesterol is reduced. Structural fragility therefore arises from the cumulative impact of multiple bends within the fatty acid chain. These bends prevent tight packing, create points of mechanical weakness, and increase susceptibility to chemical modification. The membrane becomes less able to maintain its role as a controlled boundary, and the processes that depend on that boundary begin to operate under less stable conditions because the physical framework has been altered at the level of molecular structure. Susceptibility to oxidation. Oxidation targets the double bonds within fatty acid chains and polyunsaturated lipids present multiple sites where this process can begin. Each double bond lowers the energy required for a reactive species to interact with the molecule, making initiation more likely under normal metabolic conditions. When a reactive species encounters one of these sites, it extracts an electron and creates a lipid radical. This altered molecule no longer behaves as a stable component of the membrane. Its structure shifts, and it becomes capable of reacting with neighboring lipids, extending the process beyond the initial point of contact. Propagation follows initiation. The lipid radical reacts with adjacent fatty acids, particularly those that also contain double bonds, transferring the instability across the bilayer. This creates a chain reaction in which multiple lipids are converted into oxidized forms. These products do not align with intact lipids, disrupting packing and increasing spacing within the membrane. As this disruption spreads, permeability rises, and the membrane loses its ability to maintain controlled separation between compartments. The rate and extent of this process depend on both composition and organization. A membrane with a higher proportion of polyunsaturated lipids provides more reactive sites, increasing the probability of initiation and the speed of propagation. Reduced packing density allows reactive intermediates to move more freely, facilitating the spread of damage. In contrast, a more ordered membrane restricts movement and limits the reach of these reactions, containing them to smaller regions. Oxidative products alter membrane behavior beyond structural disruption. They change how embedded proteins interact with the bilayer, affecting receptor activity, ion channel function, and transport processes. These changes are not uniform. They vary depending on the location and extent of oxidation, introducing variability into systems that rely on consistent conditions. Signaling pathways become less predictable as the physical environment shifts in response to chemical modification. Repair mechanisms attempt to remove oxidized lipids and replace them through remodeling cycles. Enzymes identify altered molecules and extract them from the membrane, directing them toward processing pathways. New lipids are then synthesized and inserted to restore structure. This process requires energy and depends on the availability of suitable replacement components. When the rate of oxidation exceeds the rate of repair, damaged lipids accumulate and structural disruption persists. Antioxidant systems operate within the membrane to interrupt propagation. Lipid-soluble molecules can neutralize reactive species and stabilize radicals before they spread. Their effectiveness depends on distribution within the bilayer and the degree of structural organization. In a more disordered membrane, these systems are less able to contain reactions, allowing damage to extend further. Susceptibility to oxidation, therefore, reflects both the number of reactive sites and the structural context in which they exist. Polyunsaturated lipids increase the likelihood that oxidation will begin and propagate, altering membrane composition and behavior. When this process is not contained and resolved efficiently, the membrane loses consistency, and the systems that depend on it operate under conditions that no longer support stable function because the lipid environment has been chemically modified and not fully restored. Signal amplification versus signal distortion. Signal amplification and signal distortion emerge from the same physical property of the membrane, how easily components can move, cluster, and interact within the bilayer. Movement allows receptors and signaling molecules to concentrate, increasing local activity and strengthening output. At the same time, excessive movement removes the structural constraints that keep these interactions specific, allowing signals to spread beyond their intended boundaries. The difference between amplification and distortion is not the presence of movement itself, but whether that movement remains confined within a structure environment. Amplification begins when receptors and associated proteins are able to assemble into localized groups. Controlled fluidity allows these components to migrate toward one another and form clusters that increase the probability of interaction. Once clustered, signaling cascades proceed more efficiently because the necessary components are already in proximity. This reduces the time required for activation and increases the strength of the response relative to the initial input. The membrane acts as a platform that concentrates activity, allowing small signals to produce meaningful outputs. This process depends on structural boundaries. Clusters must form within defined regions and remain stable long enough to complete the signaling sequence. Saturated lipids and cholesterol provide the framework that limits how far components can move and how long clusters persist. Within this framework, monounsaturated lipids allow the mobility required for assembly. When this balance is maintained, amplification remains localized and proportional to input. Distortion occurs when this balance shifts toward excessive fluidity. Increased movement allows signaling components to interact more frequently, but without the constraints that define where and when those interactions should occur. Receptors cluster unpredictably, signals spread across larger areas of the membrane, and the system begins to generate outputs that are not directly tied to specific inputs. The signal is no longer amplified in a controlled way, is expanded beyond its intended scope. This distortion affects both timing and intensity. Signals may initiate prematurely because components encounter one another too easily, lowering the activation threshold. Once initiated, they may persist longer than intended because clusters do not disassemble efficiently. The result is a loss of temporal control, where signals overlap or continue beyond the conditions that trigger them. This reduces the ability of the system to distinguish between different inputs. Electrical signaling is also influenced by this shift. Ion channels depend on precise structural conditions to open and close in response to specific stimuli. Excessive fluidity alters these conditions, affecting how channels transition between states and how long they remain active. This introduces variability into electrical signals, affecting propagation and coordination across cells. The products of lipid oxidation further contribute to distortion. Altered lipids disrupt packing and create regions with inconsistent properties, increasing variability across the membrane. These regions behave differently from surrounding areas, creating uneven signaling environments that amplify some signals while suppressing others. The membrane loses uniformity, and signaling becomes dependent on local structural conditions rather than consistent global properties. Amplification, therefore, represents controlled concentration of activity within a stable framework, while distortion represents the loss of that framework, allowing activity to spread and persist without constraint. Both arise from the same underlying mechanism of movement within the membrane, but their outcomes diverge based on whether that movement is contained by sufficient structural organization. When the membrane maintains this organization, signals are strengthened without losing specificity. When it does not, the system produces outputs that no longer correspond accurately to input because the structural conditions that enforce precision have been disrupted. When and where they are appropriate. Polyunsaturated fats are not uniformly destabilizing or uniformly beneficial. Their appropriateness is determined by where they are placed within the system and what functional demand exists in that location. The same structural properties that increase fluidity and susceptibility to oxidation also enable rapid signaling, deformation, and responsiveness when those properties are required and properly contained. The question is not whether they should exist, but where their characteristics align with the demands placed on the membrane. High-turnover signaling environments represent one of the primary contexts where polyunsaturated lipids are functionally appropriate. In membranes where rapid receptor movement, vesicle cycling, and signal propagation occur, increased fluidity allows components to reorganize quickly. This is relevant in synaptic regions, immune cell interfaces, and other areas where transient, high-frequency signaling is required. In these locations, the system compensates for structural fragility through increased turnover and localized control mechanisms that replace damaged components and limit the spread of instability. Localized signaling domains provide another context. Polyunsaturated fats can be concentrated within specific microdomains where their mobility supports signal initiation and amplification. These domains are not the entire membrane. They are constrained regions within a broader structural framework dominated by more stable lipids. The surrounding structure limits how far the increased fluidity extends, allowing the system to benefit from rapid signaling without compromising global membrane integrity. This compartmentalization is critical. Without it, the same properties that enable signaling would introduce instability across the entire bilayer. Precursor roles in signaling pathways also define appropriate placement. Polyunsaturated fatty acids serve as substrates for the generation of signaling molecules. Their presence within membranes allows rapid release and conversion when needed. This function requires accessibility rather than structural dominance. The membrane must contain enough of these lipids to supply signaling pathways without allowing them to define the overall physical state of the bilayer. This balance ensures availability without sacrificing stability. Situations requiring rapid structural remodeling can also justify increased polyunsaturated content. During processes such as cell division, migration, or immune activation, membranes undergo significant deformation and reorganization. Increased fluidity facilitates these changes, allowing the membrane to reshape without fracturing. These conditions are temporary and localized. Once the demand subsides, remodeling cycles adjust composition back to a more stable baseline. Appropriateness is therefore conditional on containment and turnover. Polyunsaturated lipids function within systems that can replace them quickly, limit their distribution, and buffer their effects through surrounding structural elements. When these conditions are met, their properties support specific functional demands without destabilizing the membrane as a whole. When these conditions are not present, the same properties become liabilities. Widespread incorporation into membranes that require long-term stability increases permeability, susceptibility to damage, and variability in signaling. The membrane loses its ability to maintain consistent conditions, and processes that depend on controlled boundaries begin to degrade. Polyunsaturated fats are therefore appropriate in contexts that demand rapid movement, localized signaling, and dynamic restructuring, provided that these contexts are constrained within a stable framework. Their role is not to define the membrane, but to support specific functions within it. When their distribution expands beyond these controlled environments, the balance shifts, and the structural conditions required for consistent function are no longer maintained because the system has replaced containment with unrestricted mobility.